Welcome to the Rosny College Electronics series of videos. Today we'll be looking at Boolean algebra, the symbols that we use in circuit diagrams, and how to represent those as Boolean expressions, which is a mathematical representation of the logic. I'll start with the AND gate. An AND gate has a symbol that, if we have a two-input AND gate, the symbol looks like that. And we have two inputs, A and B, and generally we call the output Q. However, these are notional. It could be anything, so it could be C, D and E. It could be our inputs and output. With an AND gate, we can represent this symbol, this circuit diagram, with an algebraic expression. Often it's easier to represent them as algebraic expressions, and it would look something like this. A, and we use a dot for AND, B equals Q. If I were to use a NAND gate, which is simply an inverted AND gate, the symbol looks very similar, except like the AND gate, it's the same shape and size, let's still use the same variable names, but the main difference is an AND gate has a not on the output. Looks like a circle. Zoom in on it. Okay, so this is the main difference to indicate between an AND gate and a NAND gate. So an AND gate just has the output there, and a NAND gate has the circle on it to indicate that it's inverted. And the Boolean expression for that is very similar. It's A and B equals, but to make it inverted, we want to not the output of this, so we put a bar across the top, so the bar indicates that it's inverted. Okay. So I'll draw a NOT gate now. So a NOT gate is similar. It's a triangle, but it's got a little knot on the end of it, a knot on the output, but it's different in that it's only got one input, so A and Q. So the input here, it is inverted, meaning that the whatever the value it is flipped to the opposite value. So if it's a 1, it's flipped to a 0. If it's a 0, it is flipped to a 1. So the way we write this is A, and we put a bar across it, equals Q. So you can see where the bar comes from for both the NOT gate and the NAND gate. That means the output is inverted, or swapped with the opposite. To make a NAND gate from an AND gate, I simply could do this. Have an AND gate, and then a NOT gate following it. Okay, so if I've got two inputs A and B, then that output, which I'll call C there, that's an intermediate variable. I'll take C, so C equals A and B, and Q is my output. Q equals not C. So if I did the bar over this thing, not C is going to be not A and B. So equals A and B. Okay, so you can see the NAND can be made from an AND gate followed with the output of the AND gate going into a NOT gate and giving us an inverted output of that, or a NAND output. Interestingly, if I were to do two in series, so like this is A, becomes B, so B equals not A, and Q equals not B. So therefore, if I took the knot of a knot. So I took the knot of B, did the same again. That's equal to A. So if I take the inversion of an inverted value, so I go from 1 to 0 and then back to 1 again. So I end up with the same thing. So this one, the output is going to be A equals Q. So we call this a buffer. A third type of gate is an OR gate, and that has a symbol looks like this. So all of the symbols I'm going to be using today have two inputs, and this is an OR gate. And the way we can represent that is A, and it looks like a plus, B equals Q. So it's my two inputs A and B, my output Q. A or B is equal to Q, so represented here. Similarly, we can have a not in the output of this, so it becomes A nor B. This is a nor. Again, A or B, and then I'm going to take the inverted of the whole thing, so I put a bar across the whole lot. So it's very similar in idea to the AND compared to the NAND, and the construction of a NOR gate from an OR gate and a NOT gate is the same. So I could make is a NOR as well. So I could make a NOR gate using an OR gate and a NOT gate. Now so I've shown you 5 different types of gates so far: the AND, the NAND, and the NOT, the OR and the NOR. And the final one, the final pair of gates, is very similar to these in that it's takes two inputs. However, the symbol for this is a little bit different. It looks like an OR gate but with an extra bar in front, like that, extra curvy bit. Got two inputs, A and B, and the output is Q. However, this one is exclusive OR, or XOR. Okay. And what that means is the output is high when only one of the inputs is high, not when both. Unlike with the OR, the output will be high when one of the inputs or both of them is high. Or another way of putting it, the only time it will be low is when both A and B are low. This one, it will be high when only one of the inputs is high. So it's exclusively one input is high, or one exclusively or the other, but not both. And the symbol we use to represent this is A. It looks like an OR symbol, but we put a circle around it, B. So it equals Q. So that's A XOR B. And again, we can have the inverted version. Symbol's a bit ordinary. With a circle on the output. And we call this one X NOR. Exclusive NOR. So this one will be, the output will be high when both of the inputs are the same. So it's the opposite sense of this one. So the XOR, the output high when they're different, and this one the output is high when they're the same. Or alternatively, you could say the output is low when they are different. Because we're taking the high output when it's different from this and we're inverting it to make it low. And that's the 7 gates that we use, common gates, and their Boolean expression.